Okay. People starting today's class. I think we need to schedule the final exam. So as I announced on the Blackboard, so first I proposed the 4 time slots for the final exam, and then so I hope we can take the final exam on December 13th. It's a Friday. So actually, the final exam was scheduled on Monday, so maybe December 20th, but TAs and I need to participate in the conference, so we need to reschedule our final exam. So, so I proposed the 4 times slots on Friday, but some students already emailed me that those time slots are not available. So I also suggested another 2 time slots. So it's Thursday night, and those are first Thursday night and Friday night. So those time slots are okay. So it's available. So Thursday night means that it's 7 p.m. to 8:30 p.m. on Thursday. That means the December 16th. And the Friday night means that it's the exam time will be 7 p.m. from 7 p.m. to 8:30 p.m. on December 17th. Those time slots work for you? Okay, but another student does not work the Friday. Okay, so one student is not available. So I believe we need to take the exam on Friday night. Okay. And I hope the exam will be. I hope the exam would be to be on-site exam, but you know the COVID-19 is still spreading, and then so we live. What's it called, with Corona. So we are living with Corona, but so the bad thing is that the COVID-19 is still spreading, and then the number of infected people is increasing recently. It's dramatically increasing. So I hope that we can take the on-site exam, but I think we need to check the situation of the COVID-19 pandemic. Okay, so I think everyone is available on Friday night. So okay, so I will announce the final exam schedule on the Blackboard again. So I hope we can take the exam from 7 p.m. to 8:30 p.m. on Friday. That is the December 17th. Okay. Okay, so actually it's not easy to schedule the exam. Okay. So in the previous time, as in the previous class, we learned about the memory hierarchy. So it's a new chapter. So we conclude the chapter 4. So in the chapter 4, we learned about the processor architecture, and then in chapter 5, we will learn about the memory systems of computer systems. Okay, and then the important concept of this memory system is that memory hierarchy. Okay, so I explained that why we use memory hierarchy. So we organize hierarchical memory systems. It is because we do not have perfect memory. That means that, so what is the perfect memory? The memory should be fast. So that means that the access latency, the I believe everyone knows the terminology latency because it's related to the performance. That means the execution time. But the access latency means that the request, the read or write request is given to the memory, and then this request is serviced by memory. So that means that if the read request is given to the memory provides requested data. And then if the write request is given to the memory, then this data is stored in the memory. That is those are the services from memory. Okay. So access latency means that it's the time gap between request and service from memory. Okay. So what is the better memory? So that means that what is the good memory? It's if the access latency is low, then it's good memory. It's a good memory. And then another property of the good memory is that is high density. So that means that in the same area, more data can be stored. That means the high density. And then so cost is important. Cost is important. So we need cheap memory, but access latency is low. That means the fast memory, and then the memory supports the high density, and then also the cheap memory is the perfect memory. But we do not have this perfect memory, so we use memory hierarchy. So why can we use memory hierarchy? It was very important. Why can you use memory hierarchy in our computer systems? Why? It is because our applications, the normal applications, exhibit data locality. So data locality means that you need to remember the concept of the data locality. It's very, very important in the computer systems. Okay. This data locality is very critical for the performance of computer systems. Also, it's critical for some performance of your application. Okay. So why can you use this memory hierarchy? Because our normal applications exhibit data locality. The data locality means that there are two types of data locality: temporal locality and spatial locality. So also you need to remember the definition of temporal locality and the spatial locality. So if you do not remember this definition, then you need to review you need to review previous class. Okay. So also we learned about the hit and miss in the memory level. So we learned about some various technology of memory systems. Also, this is also important. So in the previous class, I explained about the memory level parallelism. Okay, so that means that the memory is composed of multiple banks. Okay, so bank means that the memory component that works independently. So what is the definition of a bank? So here you can find the bank. So bank means that it's a memory component. It's a component. But this component works independently. Okay, that works independently. Okay? So actually, most of the memory systems have multiple banks. So why do we use multi-bank system? It is because memory is slow. So usually the processor is very fast, and then the processor give request to memory systems. But usually the memory is slow. The slow memory and the fast processor. So but we want, the processor wants to get the service from the memory with the high performance. So because the memory is slow, we assign multiple memory components that work independently. Then we can give, the processor can give request to these multiple components step by one by one. Okay, so in the first time slot, the processor can give request to the first component of the memory system, and then in the next time slot, the processor can give the second request to the second component of the memory systems. This is the multi-bank memory systems, and then so the processor can send multiple requests in a very narrow window, time window. Then even then the process also receives the multiple data, that means some services from multiple banks one by one, for one by one sequentially. Okay, so this is the multi-bank system, and then this concept is called the memory level parallelism. And then with this memory level parallelism, we can enjoy some the high bandwidth. That means that the memory can support the high bandwidth data transaction between processor and memory with the narrow memory bus. Okay, so this is the interleaved memory organization. So with this interleaved memory organization, then we can increase the performance of memory system. It's very slow, but we can increase the performance. Okay. Also, we'll briefly learn about the storage systems. The storage system is very slow, but the unique feature of the storage system is that the data is non-volatile. So non-volatile. So that means that the data is not removed even though the system is turned off. Okay. Okay, so in this time we will learn about the cache. Okay, it's also very important topic in the memory systems. So please, please try to understand the concept of cache memories. Okay. Okay. So this slide shows the definition of cache. So I searched the cache, the definition of the cache in the dictionary.com. So these are the definitions of cache. So what is the definition? So actually in our normal life, the cache means some hiding place. So like it's a 비밀금고. So like a 비밀금고. So that cache means just a hiding place. But this hiding place cannot explain the cache memories in computer systems. So we need to focus on the definition of cache in the computer systems. So what is the definition of a cache in the computer systems? This definition, okay? So what is the definition of a cache? A temporary storage space or memory that allows fast access to data. Okay, so example is the CPU cache. So what are the property of cache memories? It's a temporary storage space. So in the chapter 2, we learned that this is the instruction, and then if the instruction is given to the computer system or processor, then the computer processor execute this instruction and generate the defined result. And then I explained that the defined result is stored in the register file and main memory. Okay, so if this data is changed by instructions, then that means that the state of computer system is changed. Okay, it's changed by instruction. Okay, so data is stored in the register file and main memory. So we do not call this is temporarily. We do not say the data is temporarily stored in the register file and main memory. So do you understand what I said? So when the instruction is executed, the data is stored. So that means that the data inside of a register file and main memory is updated. So that means the data is just stored, okay? But we do not say data is temporarily stored in register file and main memory. So we need to focus the word temporarily, okay? So cache is the temporary storage space. Just to remember that the cache is temporary storage space, okay? So if the instruction is executed, the data inside of a register file and main memory is just updated. But the data is also updated in cache memory, but that is the temporary update or temporary store. Okay, just to remember that. Just to remember this. And then for what? We use cache memories for fast accesses to data. What is important? Fast. So in this definition, then we can find the two main properties of cache memories. It's temporary and fast, for fast accesses. Okay, so cache memory is actually used for improving the performance of computer systems. Okay, so in the chapter 2, I explained that when the instruction is executed, then data inside of a register file and main memory are updated. I did not mention cache. Okay, so actually the cache is the updates in cache are not result of instructions. You may be confused, but those so how can I explain? Because the cache is the temporary storage, And then when the instruction is executed, the data inside of cache can be also modified. But we can say that when the instruction is executed, the data in the register file and main memories are finally updated. So actually, that means that this cache is managed by computer processor, not by instruction. So we need to distinguish this. So we need to say that the cache is updated by processor, not instruction. And then the register file and main memory. So actually it's updated by hardware, but actually the final update to register file and the main memories are managed by, so updated by instructions. So that means that it's software. But the content inside of a cache, so that means that the data inside of cache is managed by hardware. Okay. For what? For fast accesses. So we can say that the data inside of the cache memory is managed by computer hardware automatically, not by instruction. And then the processor manages the data inside of a cache for improving the performance. Okay. This is the two main properties of cache memories. Okay, so I also added the definition from Wikipedia. So actually, if you want to know the definition of terminology, like in the computer systems or computer engineering areas, I recommend you to use Wikipedia, not Naver or DOM. So actually, so you can find some valuable information or valuable knowledge from Wikipedia or Google, so not Naver or not DOM. Okay, so I just copied the definition of cache memory from Wikipedia. So what is the definition? So cache is a hardware or software component that stores data, but so that future requests for that data can be served faster. Future request. So it's very similar to locality. So what is the definition of locality? The neighbor data or the same data can be accessed again in the near future. Okay, so that means that the locality means that the data can be accessed in the near future. So why do we use cache? The cache stores the data, and then this data is stored temporarily. Okay, and then this data is also managed by hardware automatically, not by instruction. Therefore, what? The computer processor, the computer hardware, assume that, oh, this data can be accessed in the near future. Okay, so if we expect that, oh, this data can be accessed in the near future, and then if this data is stored in the cache memory, so and then this cache memory is faster than the main memory. So, and then if it, the data which is expected, the data is requested in the near future is stored in the cache memory, then we can access this data very quickly. Okay, this is the purpose of cache. Okay, so actually this is a very important concept in the computer systems. Then this concept is also used for software, not as well as hardware. So you need to remember the concept of cache or caching. Okay, so cache means the hardware or some temporary storage space by software. Then caching means some behavior that stores data temporarily for fast access. Okay. So also I frequently use the $sign for cache because the pronunciation of cache is actually the same to the pronunciation of cash, money. Okay, so I frequently use this sign, okay, $sign. Okay, so I will explain I will explain the analogy of cache in our real life. So actually, this concept of caching is frequently observed in our real life. So can you see in this figure? So it's June. It's June, so I believe. So everyone is silent in the Zoom lecture. So in this figure, we can find that there are many books in the bookshelf, and then also we can find several books on the desk. Also, we can find a few books on this desk, and then the book is opened on the desk. Okay. So let us assume that you are preparing final exam. So that means that you need to study using your textbook. So actually in the library or bookshelf, there are many books regarding computer architecture. But when you study for final exam, you need just several lecture slides and textbook. So you just require a small number of books. But in our real life, there are a large number of books, and then we store these books on our bookshelf or in libraries. Okay, so that means that we can use these books if required, but these many books are just stored in the bookshelf or library. And then if we just want to read some books, then we just move the required books on the bookshelf to our desk. Okay, so why? Because we can read, so we can find the required pages where we can read the required materials quickly if the book is the required books are found on the desk. So what does that mean? We just, in order to study efficiently, we just move several books on the desk, and then we just read the required book on the desk. but there are many books on the bookshelf. Okay. So why do we move these books from the bookshelf? Because we want to access the required books very quickly. Okay, it will take time if we just find the required books under this large bookshelf, but if we just access this large bookshelf whenever we want to read some required books, then it will be very inefficient. It is because it will take long time. But if we can find the required books on the desk, then we can access these books very quickly. This is the analogy of cache. So this large bookshelf is the main memory. So we can store the actually large amount of data in the main memory. But as we learn, this main memory is very slow. So we can, so how can we move the required data from the main memory? So this is the RF, so it's register 5. So actually the data is moved from main memory to the register 5 by load instruction. Okay. But under this, so that means that with the load instruction, so let us assume that we want to read the computer architecture book, is a computer, our textbook from the bookshelf. So we just move the computer textbook, is a COD books from the bookshelf to our desk. Okay. So this is the load instruction. And then let us assume that we want to read another book. So we can just use the another load instruction, but with this load instruction, we need to just move this book from the bookshelf, and then the textbook, so COD book, should be returned to the bookshelf. Okay. So problem is that it will take a very long time, and then we frequently want to use our textbook again and again. So in this case, we can just store our COD book, it's a textbook, on the desk. Then if this COD book is required again, then we can just find the textbook from our desk, and then we can just read the required page on this textbook. Okay, it will be more efficient. Okay, so this is the analogy of cache. So this is the main memory. This is a large bookshelf is the main memory, and then some books. So required page is the kind of registers in the processor, and then these books is the cache, the data inside our cache memory, and then we can access these books if required. Now, what's the problem? So how can we? So the problem is not the problem. Then how can we increase the efficiency of our study? So these books are cache, and then this is the bookshelf is the main memory, and then this is the register file. So how can we increase the efficiency of our study? The efficiency is related to how frequently required books are found on the desk. What does that mean? So if the required books are frequently found on the desk, that means the cache, then we can increase our efficiency. It's same, okay? It's obvious, okay? So the data is, so data, actually the data is transferred to the register file by load instruction. That is the request, okay? So if the load instruction is executed, so that means that the request data, so that means the request book is requested from the main memory, so like bookshelf. But these request data can be found on the main memory, or also the request data can be found in cache memory. So if we already move the required book to this cache memory, then we can find this requested data on the cache. And then if the request data is found in the cache, then we can transfer this data to the register file very quickly, because the cache is faster than the main memory. Okay, so the requested data is found in the cache, which means it's hit in the cache. So in order to increase the efficiency, so that means that in order to increase the performance of our computer systems, then we need to increase the hit ratio of cache. Okay, so I explained that the efficiency is proportional to the how frequently the requested data is found in the cache. Okay, so how frequently the required books are found on the desk. It's the same to the how frequently the requested data is found in the cache. Okay, so how frequently found in the cache is related to the hit ratio. So we learned in the previous class. Okay, so we need to increase the hit ratio, okay, to improve the performance of computer systems. Okay, so I hope everyone can understand the analogy of cache. Okay, okay. So let's see how cache works. So cache is also memory. So what is the memory? So actually you are requested to design single cycle processor. Then so you can find the instruction memory, or register file, and data memory. So how memory works? So memory has address port, and data input. Oops. Data in and data out. And then the data is stored in the entries in memory. Okay. And then the location of the entry. The location of the entry is indexed by what? Address. Okay. So in a high-level language like A equal 1, so that means that this data 1 is stored in the variable A. Okay, in the high-level language, high-level code, but in a computer system, so we already learned that the data is, if this statement is executed inside of the computer system, so that means the data is stored in a certain space in memory, and then this space is identified by address. So actually in the computer system, this A, the variable name A, has the address, is actually the pointer of A, and then the data is stored inside of this memory indexed by address. Understand? So what does that mean? The data is stored in memory, like main memory or register file, so all kinds of memory. And then we can identify this data with address. Okay, so this is the entries of memory, and then if we just access a certain entry with the address, then we can read or write data using this address. Okay, so we can use this address for ID, identification of the data. It's similar to the citizen ID of people in our nation. So we can distinguish, so we can identify people with their citizen ID, 주민등록번호. So, which means we can identify the data with the address. Okay, so that means that we can use the address like citizen ID for people. Okay. And how can you access the data? If the address is given to the data for read, then the data is provided from the memory. And then if the address is given to the memory, and then the data input is also given to the this memory, then this space corresponding entry of the memory is updated by input data. Okay, that's how memory works. Then how about the cache? So cache is actually temporary memory. And then what is the actual memory? Actual memory is the main memory. So temporary memory means that this is the large memory, and then cache memory is the small memory. We just store the part of data from the main memory to the cache. For what? We expect that, oh, this data can be accessed in the near future. So if we can find this request data, so this data in the cache memory, then we can access this data very quickly. For this purpose, we use cache. Okay, then how can we store data inside of the cache? So that means that how can we identify the data inside of the cache? Okay, there's no interaction. So this is the large memory. Actually, this data can be identified by address. So what does that mean? So when we also part of data is stored in the cache memory for fast access, then we can just store ID of the data and data. So why do we need this ID? We use the load instruction like load x1, 0, x2, and this is the address of data. So that means that with this address, with this load instruction, just request the data from the main memory. So that means with this address, so this is the address, the main memory just provide the data inside of this memory identified by this address. But I said that the same data can be found in the cache. If this data is stored in the cache, in the past. So how can we identify this data? If the cache memory also stores the ID of this data, like ID means the address, and its own data is also stored in the cache, then we can just check this address is the same to the address stored in the cache. Then we can figure out that the request data exists inside of the cache. Do you understand? So what does that mean? When the data is temporarily stored in the cache memory, so the cache memory size is much smaller than the main memory. And then to identify the request data inside of cache, then we need to store also address of data. Okay? Understand? So I want to explain that when the data is stored in the cache, the address of data is also stored, is logged in the cache. Then by checking this stored address of data, then we can figure out if the request data exists in the cache or not. Okay. Then the first, I explained that how to identify data in cache. Then the second issue is which data is stored in the cache. So first, I explained that how to identify data inside of the cache. Then the second is that which data will be stored in the cache. So why this second topic is important? So I said that if the cache has high hit ratio, then we can increase the performance. What is the high hit ratio? High hit ratio means that the request data is more frequently found inside of cache. So that means that that's why which data will be stored in the cache. Which data? So I explained about the locality. So what is the definition of the locality? The neighbor data, if a certain data is accessed, then a certain data is requested by processor. And in the near future, the same data, that is the temporal locality or neighbor data, is the spatial locality, can be accessed in the near future. This with a high probability. That is the definition of a locality. And I said that in our normal application, we can observe locality, data locality in our normal applications. So that means that if a certain data is accessed, then neighbor data or the same data can be re-accessed. That means that accessed again in the near future. So which data should be stored in the cache? So how can we increase the hit rate or hit ratio in the cache? So based on the locality, the same data or the neighbor data to be stored in the cache. Right. It's reasonable, right? So how can you store the same data? So it's simple actually. It's a load instruction. If a certain data is requested by load instruction, then the same data also can be stored in the cache. Okay, and then with the high probability, we can expect that the same data can be accessed again in the near future. So that means if a certain data is requested by load instruction or store instruction, then this data can be stored in the cache. Okay, and then for this spatial locality, how can we exploit the spatial locality? How can we store the neighbor data? So we can think like this. This is the load instruction, actually load double word. So with this load instruction, we just transfer 8-byte data, right? But when this load instruction is executed, and if processor transfer the more data from the main memory. So for example, when this load instruction is executed, so this load instruction just requests 8-byte data. But if we just transfer 16-byte or 32-byte data to the cache, then we can also store neighbor data to the cache memory. Do you understand what I said? So instead of just transferring 8-byte, the request size of data, we can just larger data size to the cache. In order to exploit spatial locality of data. Understand? So I explained that which data will be stored in the cache. So the same data. So if data is requested, the data is stored in the cache. Obvious. And then for the spatial locality, the larger amount of data is stored in the cache and the data is requested. So then, for example, if just 8-byte of data is requested by load instruction, but when this load instruction is executed, the larger amount of data, Like, for example, 32-bit, 164-bit data is transferred from the main memory to cache in order to exploit spatial locality. Okay, so the first topic is that how to identify data inside of the cache. So in order to identify data inside of the cache, cache also stores the address of data. And each data will be stored in the cache. Cache stores the large amount of data. And this data block is requested by processor. That means load instruction or store instruction. Okay. Okay. So this slide just explains that this which data will be stored. And the data is accessed by processor. That means that the data is requested by processor. The data is stored in the cache. So in this example, this cache memory has these data, and then when the XN is referenced, that means that the XN is requested by load instructions or store instructions. This data is stored in the cache. So then where is the cache? Where is the cache memory in the memory hierarchy? The cache is here. So this is the register file, and then as you learn, the register file is very small and very fast. And then main memory is slow and very large. And where is the cache? Cache is located between register file and main memory here. And then also the cache may have multiple levels, like level 1 cache, level 2 cache, and level 3 cache. So level 1 is close to the processor, and then level 2 is here, level 3 cache is here, like this. So what does that mean? Among these multiple levels of cache, level 1 cache is the fastest and smallest. Fast and small. And then level 3 cache is slow and large. Okay. So level 1 is closer to processor. Then level 2 cache is here. Level 3 cache is here. And then usually in the laptop processors or desktop processors, also the high performance server processors have until level 3 cache. Okay. So this cache is also called the last level cache. Last level cache. Then it's also called the LLC, last level cache. Okay. Okay, so this slide shows the architecture, pipeline process architecture we learned. And we learned that in the chapter 5, the main memory is here, and then there are multiple levels of cache, like level 1, level 2, level 3, and register 5. But in the chapter 4, we learned that, this is the instruction memory, and this is data memory. The question is that we cannot find any instruction memory or data memory in the memory hierarchy. So actually, this is the main memory, and this is the register file, and caches storage. Where is instruction memory or data memory? And then also, so these are separated memory. Why do we split the memory into instruction memory and data memory? in order to avoid structural hazard. Okay, we learned in the chapter 4. But we cannot find any instruction memory or data memory in the memory hierarchy. What does that mean? What is this? So actually, this instruction memory is level 1 instruction cache, and this data memory is the level 1 data cache. Memory. Okay. So this is the level 1 instruction cache, and this data memory is the level 1 data cache. And where is level 2 cache? So level 2 cache is here. And then the request data is not found in the level 1 instruction cache or level 1 data cache. Then the processor accesses level 2 cache here, and then try to find the request data in the level 2 cache. And then if this data is not found in the level 2 cache either, then the processor also accesses level 3 cache, okay? And then try to find the request data in the level 3 cache. And if not found, processor accesses main memory, okay? So you need to remember that this instruction memory is actually level 1 instruction cache, and then data memory is level 1 data cache. Okay, so this is the instruction, and then this is data. Okay, then let's see how the data is managed. So data is identified in the cache. So I said that in order to identify the request data in the cache needs to store ID of data. And what is the ID of the data? The ID of the data is the address. The cache also stores the address of data. Okay, and then this is the cache memory, and then the cache memory also stores this is the address, and then this is the data in the cache. But I also said that the cache memory size is small. Then we need to also consider where the data in the cache, where to store data in the cache. So what does that mean? Cache is also memories. So what's the definition of the memory? The memory has multiple entries that can store data, and then this data is stored a certain entry. Okay, so that means cache is also a memory. Cache has multiple entries that can store data, and then we need to decide where to store data in the cache. Okay. So this is the cache memories, and then cache has multiple data, and then data is accessed by processor. So with the load instruction. So we need to decide where to store this data in the cache. So that means that where this data stored in which entries in the cache. So we need to decide which entries. So this is the data. So actually there are multiple entries in the cache. So this data can be stored to this entry, or this entry, or this entry. So we need to set a rule of data allocation. So we need the rule of data allocation in cache. So that means we need to decide which entry is used for storing the data, new data. Okay. Also, the cache is memory. So in order to access the data inside of a cache, we just need the address. So that means, what does that mean? So this is the typical memory block. So in order to access this memory, we need the address, so data input port, and then data output port. And then what is the behavior of this memory? And this address is given, and then the data is out from the memory, indexed by address. So in the cache memory, let us assume that this data is stored in the index of 02 in the cache. So how can you access this data? You can just give this index number 02 to the cache memory. Then data is out from the cache. It's the same to the memory. Okay. So rule of data allocation in cache means that we just decide which index number is determined to store the data inside of cache. And then there are multiple ways. And then first we will learn about the direct mapped cache. Okay. We will first learn about the direct mapped cache. So direct mapped cache means that the part of the memory address is used for the index of the cache memory. And then a certain, so in this example, this cache has 8 entries, so we can use 3 bits for the index numbers, right? Understand? So, and then a certain index number like 001 is mapped to this is the main memory, address of main memory that has the same LSB bits, which is identical to the index number of cache. So that means in this example, the index number of this entry is 001, okay? And then this is the memory space, and then among addresses of memory, this memory space 00001, 01, 001, 001, 10, 001, 11, 001. So these 4 address spaces can be allocated to this cache entry. So what does that mean? If a data inside of this memory address is requested, then this data is can be just stored in the index number 1 of the cache. And then a certain data is also accessed for a certain data that has the address of 01, 001. And then this data can be also stored in the just index number 001. Okay. So what does that mean? This allocation index number of the cache is determined by part of address. So in this example, we just use the lower part of address in the memory for the index of the cache. So that means the data of this address, this address, this address, this address is just allocated to index number 001. And then if a certain data has the address of 00101, then we can just use this address as the index of the cache. So this data is stored in the other entries of the cache, like index number 101. Understand? This is the direct mapped cache. So with the direct mapped cache, the index number of the direct mapped cache is the lower part of the address of the data. Okay, this is the direct mapped cache. 네, yeah. So one student asked a question. So this data is firstly accessed. So this data is stored in the cache, and then in the future, this data is accessed again. This data of 0111 or 01001 is accessed, and this space is overwritten by this new data, right? Because these addresses, the data of these 4 addresses are mapped to the index number 001 of the cache. So if this data 1 is accessed, and then this data 2 is accessed, then this cache index is overwritten by data 2. 네, 맞습니다. 새 정보가 올 때마다 덮였어요. Okay, this is the direct mapped cache. So so this is the address. So this address of data, and then the bit of the address of data can be look like 00001. So the cache used the lower part of the address as the index. So this cache has the 8 entries. The cache just allocate the data of this 00001 to the index number 001 of the cache. And then how can we identify different data that has the same cache indexes? So that means that, the data of 00001 can be stored in the index number 001. 01001 also can be stored in the same index of the cache. Now, how can we identify different data that map to the same cache indexes? We can identify different data with this part, okay, upper part of the address. So in this case, we do not need to store all address bits in the cache, because this part is used as the index of the cache memory. So we can just store the remaining parts to the cache to identify data inside of the cache. Okay, so in this case, this direct mapped cache can just store the remaining part of address to identify data inside of the cache. Okay. So I will stop here, and then in the next class, I will also explain how the data is accessed in the cache, and then how data is managing the inside of the cache. Okay. So do you have any questions? 수요일은 게 수요일이 언제 수요일을 말을 하는 거죠? 22일? 네, 수요일, 그러니까 22일은 그때까지도 컨퍼런스가 계속 있어서 안 될 것 같고요. 그리고 저희가 15일까지는 수업을 해야 될 것 같습니다. 네, 그 15일까지는 수업을 해야 될 것 같고요. 22일은 네, 시간이 안 되네요. 네, 그래서 금요일 날 봐야 될 것 같아요. 금요일 날 볼 수밖에 없을 것 같아요. 네, 그럼 미안합니다. Okay, so thank you for your attention. See you in the next class.